It's really not long enough.
That would be chance it until
12 to 12:30?
11:50.
Okay.
It's done.
Do they have to all eat lunch together? Or do they let them eat? I'm sorry, I don't know, I don't make the rules.
That sucks.
I didn't know that, like, Samson School doesn't have quarters. I learned that on Monday. So they're still in semesters. Yeah. I don't know. I thought we were supposed to do the same. So it's whatever. Okay, so balancing equations is the very first thing that you need to know in topic 2. How to balance an equation. So I guess I could easily just do an example here. I'll make something up on the fly. Let's do a combustion equation. This is the easiest combustion equation you can balance, so we'll try this one. So this is an equation. To balance an equation, it's really important that we have the same amount on both sides. That's our conservation of matter. Things don't just disappear. So to do a balancing equation, we always draw a line down the middle, and then we tally up what's there. What do we got on the left-hand side?
4. So we got CHO.
CHO should be the same on the other side. If not, there's something wrong. Reevaluate your equation. Then we've got to write down how many we have of each of these. So how many C's do we got? 1. Hydrogens. 4. And oxygens. 2. Won't say anything. Can you see that? Okay, and on the left or right hand side, we've got how many C's?
We got 2.
1. Hydrogens. 2. Oxygens. 3. Okay. Yeah. Sounds good. Okay, so when we look at this, we've got our carbons are balanced, our hydrogens and oxygens aren't. So our first step is to balance probably our oxygen. We only leave our hydrogens till the end. Okay, so our oxygens, we've got 2 on one side and we've got 3 on the other. What's really important here is that we can never put a number here. Oh, my pen's off. We can never put a number right there. Something times 2 to give us 3. It can't happen. We can never times 2 and get an odd number. So what I would always do is, to avoid that, get this number to not be 3. I'm going to put it to 4. To get it to 4, I'm going to put it 2 in front of here. Okay? By putting a 2 there, we got 2 oxygens and 2 oxygens. Now we got 4. That also changes our hydrogens. How many hydrogens do we have on the right-hand side?
We got 4.
4. So we're going 2 times 2 gives us 4. All right? So now our oxygens are 4, our hydrogens are 4 on the right-hand side. That actually made our hydrogen balanced. That was lucky. So let's balance our oxygens. So we've got 4 on the right-hand side. We need to get 4 on the left. So what do we do?
That time we put a 2.
So if we follow what Kai told us, we would put a 2 in front of the O2. Is that right, Landon? Yeah? Yeah, it's right, because whatever number we put in front there, that's really bad too, it's going to be multiplied by this little number. So these 2 numbers are multiplied together, and when they're multiplied together, they give you 4. That is is now balanced. Our C's, our H's, and our O's are all the same number, so we've got a balanced equation. So if we were to write this on our test or quiz, it would be, if there's nothing there, so nothing in front, like that, it would be considered a 1. So 1, 2, 2, and then another 1, right? So don't put zeros on the little lines. It does mean it's a 1 if we don't write anything there. All right? Is that okay?
Yep.
Yeah. So that's balancing. There's lots of examples on that on when we first did this in class. So if you need more examples or if you need help with it, let me know. Our conservation of mass. So I'm just going to, I really should have put a question on here. At the very first of our topic 2 review, there's actually a question that involves conservation of mass, and I really should have put it on here. So conservation of mass is really just talking about if we have a mass of something on one side, it's got to equal the other. Just like we just said, like things have to balance. We can't just randomly have something on one side and not on the other. Okay. So I'm just going to write that actually. So we need to balance mass from one side to the other. And I'll give you an example of that. I'm going to actually open your topic 2 review. It's the first question on your topic 2 review, so maybe you've already done this. Hopefully you have. But that one is talking about conservation of mass. I guess I can't write on this. That's annoying. All right, so this question on the very first year topic 2 review is a conservation of mass question. It says, according to the law of conservation of matter, what mass of oxygen must have reacted with iron in the equation below, and explain how you know. So, I can't actually write this on here, so I'm going to just write this on my other note slide. FeO2. Okay, so as far as our law of conservation of mass tells us, from one side to the other, we should have the same amount. So if we have 3.25 grams of iron on one side, we should have 3.25 grams of iron on the other side. Because iron doesn't just go missing. It's not up in the air, per se. So what we would do to figure out how much oxygen there is we would just minus these two numbers. So to figure out, on one side we've got 3.25 iron, and then on the other side, together the iron and oxygen make 9 grams. So if we take our 9 grams and we minus 3.25 grams, could someone do that on the calculator?
It is
So 9 grams, there's a decimal there,
5.7.
5.75. So if we do that in the calculator, minus those two numbers, we get 5.75 grams. So what that means is that we must have 5.75 grams of oxygen. Because we can't just get mass out of thin air. So this 9 grams is made up of oxygen and iron. We know how much there is of iron at the first, so we must add that much grams of oxygen to get a total of iron and oxygen together. Does that make sense to you? So like, it's not coming out of thin air, we're not losing iron. This has to be a balance. So always think of this line in between your reaction as being a balance. This side has to be the same as this side. So that's just an example of how we would do a question that's conservation of mass, just showing that the mass is not changing. This question says, how do you know? Well, if you had to write something there, you might say, well, I know because we don't just lose iron into thin air. It doesn't magically disappear. What we have on one side has to equal the other. Okay? So that is an example of our conservation of mass. And I'm going to go on to our mole ratio. So for mole ratio, this is again just talking about conserving. So we need to have the same amount of each element. On both sides of the equation. Okay. So when we're talking about a mole ratio, I'm going to bring you to another example of mole ratio, which was done in the review. So maybe you've done this one, maybe you haven't, but I'd like to try one of these, maybe just the first one, to show you how you can do this. You know what, I'm going to screenshot this and open it up. I can write on it here. Okay, so to do one of these types of questions, let's just read through this question and we'll do A at least. So it says to make pure iron from its ore, iron-3 oxide must react with carbon monoxide. The balanced equation, chemical equation for this reaction is this. So Fe2O3 plus 3CO gives you 2Fe and 3CO2. So the question says, if we have 1.5 times 10 to the 3 moles of iron-3 oxide reacted with the carbon monoxide, how many moles of pure iron metal will be produced? Okay, so this might seem like, oh my god, that's crazy, there's so much things going on there. But this question is not too complicated. How we would do a type of question like this is we always take the amount of moles they give us. So in the question, they've given us 1.5 times 10 to the 3 moles. Don't know why my M went like that. Really bad. So that's moles of, and it's good to write down what it is. It's iron 3 oxide. So that's Fe2O3. Okay. So to figure out this question, we need to multiply it by the mole ratio, and that is what we're talking about right here, mole ratio. Our mole ratio is figuring out basically using the balanced equation to help us calculate this. So it's saying how much iron 3 is reacted with carbon monoxide to create pure iron metal. So whatever we're trying to create, whatever we're trying to produce, we're always going to write on the top of the equation. So it says how many moles of pure iron metal. So what is the symbol for pure iron metal? You don't have to look it up or anything. We're looking at this equation. So this is our equation up here. Which one of that equation is iron? Just iron on its own. Yeah, 2Fe. So what's really great for what Kai said is he said the 2. It's good to actually put that in there. But I'm going to just write Fe for now. So what we want to figure out is Fe. What we have is Fe2O3. So we put whatever we have on the bottom. Okay? Now the numbers that we put in front of that are the numbers that we see in the chemical equation. The numbers, they're called coefficients. They're the number right before our balanced equations. So we got Fe2O3, so there's no number right there. There's no number in front of that. So that's a 1. Remember, if there's no number, it's a 1. Can you tell that that's a 1? My terrible writing. Hopefully when I get my school iPad, I'll have better writing. So that's a 1. We also need to put the number that's in front of the Fe, and if we look in front of Fe, it's a 2. So we would write 2. Okay? Then we go and calculate this. So how we would calculate this is we take this number, multiply it by 2, and divide it by 1. So always multiply by the top, and then divide by the bottom number. That's how we would do a mole ratio question. And I'm getting you guys to do the calculations, but I can do it as well. So 1.5 times 10 to the 3. Do you guys know how to put that in the calculator? Times 10 to the 3. It's the little 10x button. And then you can put 3 in. Times 2. That's not good. Just put my... And then divided by 1. You should get 3,000. Did you get that? So one thing to note when you're doing this on the calculator, and it happened to me when I first did it. You can see my screen. See how on the very first line of my calculator screen it says, this is really bad, 1.5 times 10 to the 3, and then I put times 2. That times 2 went up into the exponent, so it messed it up. So it's better to put 1.5 times 10 to the 3 and then equals, and then do your times 2. Okay? I'm sorry, that looks really shaky. I'm not trying to be shaky, it's just trying to focus on a screen and it's not having a good time with that. So if we do that out in a calculation, I got 3,000. I hope you did too. The 3,000 is a concentration It's a moles, so we need to write moles. What is it moles of? It's moles of iron. Okay. Something to always note if you forget which one you put on which level, whatever you start out with has to go on the bottom of your mole ratio because they have to cancel each other out, so you're left with what you want. That's a mole ratio question. I'm not sure if you guys' heads hurt as much as mine, but I still have concussion symptoms, I think, so. You can go ahead and concussion. Oh. I got a concussion like 3 weeks ago. That was like some Like I was wearing these exact sandals actually, and I went to drop kick a ball, and when I went like this, the grass was wet, and it just fell backwards and just smashed my head off the ground. So yeah, the screens really hurt my head. And yesterday I just like spent so much time on the screen, my head's just like, I feel so dizzy and.
Yep. So I stayed home when I got it.
I stayed home for like 2 days, 1 week.
That
That must have been not your week. It must have been the other one. Or was your week? You totally missed out that I had a concussion.
You guys get it over.
Yeah, because it was the very first week of school and I was having, that's when I got my concussion. The day before school started. Anyway, that's an example of a mole ratio. And there's some more on your slide. I just wanted to show you an example right now, and so we can move on. So if you have trouble with that, please let me know. I can help you out. This is reduction and oxidation. So this one, it's not my favorite topic in chemistry, but it's something that we need to learn. It has a lot to do with our life because this is how batteries work. This is how electricity works. Like, we're not just teaching you this for the sake of it. It's actually useful. If you ever want to go on to do any sort of electrical work, you're really going to need to know what oxidation and reduction is. So oxidation and reduction, does anyone remember what those mean?
Reduction is, so it's electrons.
Yep. So it has all to do with electrons. Yeah.
Reduction is
I don't know.
gaining, I believe, and oxidation is losing. Oil rig.
Oops.
Yeah, oil rig.
So reduction is gaining electrons, oxidation is losing.
Yep.
Are you sure?
I believe so.
Yeah, you're right. So it's pretty sure and it's right because we always refer back to oil rig, or I do. The textbook tells you Leo the lion says or I don't know, that's some silly mnemonic that I don't understand. This is the one I learned when I was in high school, so I'm going to just teach you this one, where this will explain to you. So O, oil, is oxidation is losing. That's what it stands for. Rig, reduction is gaining. So just by remembering the word oil rig, you can remember what is reduction gaining electrons or losing electrons, and oxidation. Okay, what the heck does that all mean? Well, gaining and losing electrons from one side of a reaction to the other. So, I'll give you an example. Okay, so I'm gonna show you the example on the bottom here. I hope that there's enough room. I'll try and fit all of this in. So how would we use this information to figure out a reaction? Well, reduction and oxidation. If we're looking at a reaction, all you guys gotta do is figure out which one is being reduced and which one's being oxidized. So to figure that out, you're gonna follow an element from one side to the other. So Ag to Ag and Fe to Fe. So our main thing here is we gotta figure out the charges. What is the charge of Ag on the left? It's 1. How do we know that? Because there's a plus sign there, right? It's plus 1. So really make sure that when you're talking about this, you're using negatives and positives. So it's a positive 1. And when you follow it all along, it goes to here. Ag is a solid. This little S is telling us it's solid. What's the charge of something that's a solid? This is not something you're able to look up anywhere. This is something that you just have to know. And if Jason was here, he would be telling us what it is. He's like an expert at this.
It's 2.
It's not 2.
0.
Yeah, it is. So every single solid, whenever it has that solid, if it's a solid metal, the charge of it's 0. Metal by itself doesn't have a charge. That's why we don't get like shocked when we touch metal, right? There's no charge with that.
Makes sense.
It's solid metal. Huh? Okay. We shouldn't get shocked if we touch metal. If we get shocked when we touch metal, that means that it's charged. That means you're gonna go electrocuted, right? So solid metal should not have a charge. So that means the charge of this one is 0. The charge of this one is plus 1. So if we follow silver from one side to the other, it went from plus 1 to 0. Is that becoming more positive or more negative?
It'd be more positive.
If I separate this, Ag is going from plus 1 to 0. That's becoming more negative. Right? Because past 0 is -1. If you think of like a number line. So Ag is more negative. And when something becomes more negative, that means that it's gaining electrons. Okay. Okay, perfect.
Why?
So something that's gaining electrons is becoming more negative because electrons are negative. Alright? So if we look back at our thing, gaining electrons is oil rig right here. Gaining is reducing. Okay. Check the Fe. What's the charge of Fe solid? 0. What's the charge of Fe on the other side? Plus 2. From one side to the other, it's becoming more positive, right? When you become more positive, you lose electrons. So this is losing. But electrons are negative. So when you lose those negatives, you become more positive. When you lose those electrons, that's oil rate, oil oxidation. Okay?